Something might be racing toward Earth at this exact moment, a beam of radiation powerful enough to sterilize every living thing on the planet's surface, and by the laws of physics, there is absolutely no way to see it coming. Not because our telescopes are too weak, not because it's too far away, because the beam travels at the speed of light itself. The first photons that could warn us arrive at the same instant as the photons that kill us. No advance notice, no time to react, just sudden mass extinction from a direction we never thought to fear. This isn't science fiction. These beams exist. They're called gamma-ray bursts, and they're the most violent explosions in the universe since the Big Bang itself. In a fraction of a second, a single gamma-ray burst releases more energy than the sun will produce in its entire 10-billion-year lifetime. And that energy gets focused into a narrow jet, like a cosmic searchlight sweeping across the universe. If Earth happens to be in that beam's path, from a source close enough, everything changes instantly. The strange part? Humanity discovered these things by accident while looking for something else entirely. In 1963, the United States launched a series of satellites called Vela. Their mission had nothing to do with astronomy. They were nuclear watchdogs, designed to detect secret Soviet atomic bomb tests in space, which had been banned by treaty that year. The satellites carried gamma-ray detectors because nuclear explosions produce a distinctive gamma-ray flash. For 4 years, the Vela satellites faithfully watched for Soviet cheating. Then, on July 2, 1967, Vela 4 detected a gamma-ray flash, but it didn't match any known nuclear signature. The pulse came from deep space, and it was far, far too powerful to be any bomb. The military classified the detection. Over the next few years, more flashes appeared, seemingly random in direction and timing, each lasting anywhere from milliseconds to several minutes. By 1973, when the observations were finally declassified and published, astronomers had 16 of these mysterious bursts on record. The paper's dry title concealed genuine bewilderment. Nobody had any idea what could produce such staggering energies. Here's the scale problem that made gamma-ray bursts so baffling. A gamma-ray burst briefly outshines the entire observable universe in gamma radiation. That's not hyperbole, it's measurement. During that fraction of a second, more gamma-ray energy pours out of one point in space than from all the hundreds of billions of galaxies combined. To generate that much energy requires something catastrophic happening to something massive. But what? For 2 decades, the leading theories assumed these bursts came from relatively nearby, perhaps from the edges of our own Milky Way. That would keep the energy requirements somewhat reasonable. If the sources were billions of light-years away, the energies would be impossible to explain. In 1997, Italian and Dutch astronomers finally caught a gamma-ray burst in the act with enough precision to identify its host galaxy. The source sat at a distance of 6 billion light-years. The energy requirements jumped from implausible to absurd, unless something was focusing that energy into a beam. This is where the physics becomes both terrifying and elegant. Imagine squeezing the entire energy output of a star's collapse into a jet only a few degrees wide. Instead of radiating equally in all directions, almost everything gets channeled into 2 narrow beams shooting out from opposite poles. An observer anywhere else in the universe sees nothing. But if you happen to be staring directly down the barrel of that jet, and only then, you witness the most luminous thing that has ever existed. The beaming effect explains the energy budget. The total energy is enormous, but not infinite. It just gets concentrated like sunlight through a magnifying glass. The beam's opening angle is typically between 2 and 20 degrees. Run the geometry. If gamma-ray bursts spray randomly across the sky, we only see the tiny fraction aimed at us. For every burst we detect, roughly 500 others fire into directions we never notice, which means the actual rate of gamma-ray bursts in the universe is roughly 500 times higher than what we observe. They're happening constantly. Right now, somewhere, a beam is firing. So what creates these jets? The answer splits into two categories, depending on how long the burst lasts. Long gamma-ray bursts, lasting more than about 2 seconds, come from the deaths of extremely massive stars. A star at least 30 times the Sun's mass exhausts its fuel and its core collapses directly into a black hole. The surrounding stellar material tries to fall in but carries too much angular momentum. It spirals into a disk instead. That disk, superheated to billions of degrees, launches twin jets along the rotational axis at 99.9% the speed of light. The jets punch through the dying star's outer layers and scream into space, producing gamma rays through internal shocks where faster-moving material catches up to slower-moving material and collides. Short gamma-ray bursts, under 2 seconds, come from an even more violent origin, the collision of two neutron stars. These are the crushed cores of dead stars, each packing more mass than the Sun into a sphere only 20 kilometers across. When two neutron stars spiral together and merge, they briefly form a hypermassive object that collapses into a black hole within milliseconds. Again, jets launch. Again, focused destruction. In August 2017, gravitational wave detectors caught the space-time ripples from two neutron stars merging 130 million light-years away. Telescopes across the electromagnetic spectrum watched the aftermath. It confirmed the connection between neutron star mergers and short gamma-ray bursts directly. Now bring this home, to Earth, to you. If a gamma-ray burst occurred within roughly 6,500 light-years of Earth and its jet pointed directly at us, the effects would be catastrophic. The gamma rays themselves wouldn't reach the surface. Earth's atmosphere absorbs them high up, but that absorption is exactly the problem. When gamma rays slam into atmospheric nitrogen and oxygen, they shatter molecules and trigger chemical reactions that produce nitrogen dioxide and destroy ozone. Within seconds of a nearby burst, somewhere between 1/4 and half of the ozone layer would be gone. Ozone shields life from the sun's ultraviolet radiation. Without it, DNA damage rates skyrocket. Surface photosynthesis collapses because the organisms doing it, phytoplankton, plant, get sterilized by UV. The food chain breaks from the bottom. Meanwhile, nitrogen dioxide rains down as nitric acid, acidifying oceans and soil. Paleontologists have wondered for years what caused the Ordovician extinction, roughly 445 million years ago. Over half of all marine species vanished, yet there's no obvious impact crater, no massive volcanic province from that time. Some researchers have proposed a gamma-ray burst as the culprit, a cosmic sniper shot that left no bullet to find, only the damage pattern. The Ordovician extinction preferentially killed shallow water species, while deep ocean creatures survived better. It preferentially killed species in the tropics and mid-latitudes, while polar species fared better. Both patterns match what gamma-ray burst models predict. UV damage would be worst where sunlight is most intense. This remains a hypothesis, not proof, but it's physically consistent. So the natural question, could it happen again? Within our galaxy, there's a star called WR104, located about 8,000 light-years away. It's a Wolf-Rayet star, a massive, unstable beast shedding its outer layers in violent winds. Wolf-Rayet stars are exactly the progenitors of long gamma-ray bursts, and WR104 is in a binary system, its rotation axis roughly, though not precisely, aligned towards Earth. Roughly is doing a lot of work there. The jet's opening angle is narrow. If the axis is tilted even 10 degrees away from us, we're safe. Current measurements have large uncertainties. We simply don't know exactly where WR104's poles point. But the statistics offer some comfort. Long gamma-ray bursts preferentially occur in galaxies with low metallicity, few heavy elements. The Milky Way is metal-rich by cosmic standards. Our galaxy's stars contain enough heavy elements to steal angular momentum from collapsing cores, preventing jet formation. The rate of gamma-ray bursts in galaxies like ours is probably below 1 per million years. Make a rough estimate. Take a dangerous radius of 6,500 light-years. Calculate how many stars lie within that volume, perhaps a few 100 million. Assume Wolf-Rayet stars constitute maybe 1 in a million of all stars. Apply the metallicity suppression factor. Apply the beaming geometry. The probability of a direct hit on Earth in the next 100 million years is somewhere between trivially low and worth worrying about. Different assumptions give different answers. The honest summary: unlikely, not impossible, and not something we can control. Which raises a strange philosophical point about gamma-ray bursts. Most existential threats, asteroid impacts, supervolcanoes, climate catastrophe, can theoretically be predicted or mitigated. Gamma-ray bursts cannot. The warning travels at exactly the same speed as the weapon. No amount of technology changes this. If a beam is coming, it arrives with its own announcement. Astronomers sometimes describe gamma-ray bursts as the universe's way of enforcing humility. There exist dangers that cannot be prepared for. There exist events so far beyond human scale that our survival depends entirely on geometric luck, on not being in the wrong place when the beam sweeps past. And yet, the science of gamma-ray bursts keeps revealing new structure, new subtlety. In recent years, observations have shown that jets aren't perfectly uniform. They have angular structure, with more energy near the axis and less at the edges. This complicates the statistics. It also means slightly off-axis bursts might deliver damaging but non-lethal radiation doses, a scenario that could cause elevated cancer rates and crop failures without full extinction. Modern gamma-ray observatories, satellites like Swift and Fermi, detect roughly 1 burst per day. Each one, arriving from billions of light-years away, represents a jet that happened to point at us from a source too distant to matter. They're postcards from catastrophe, harmless only because of the inverse square law. Intensity drops with the square of distance. Double the distance, quarter the flux. 8,000 light-years is uncomfortably close. 8 billion light-years is a fireworks show. The deepest open question isn't whether nearby bursts are dangerous, they clearly would be. It's how the rate varies with cosmic time. Early galaxies had lower metallicity, meaning more gamma-ray bursts. Some researchers argue that gamma-ray bursts may have prevented complex life from arising anywhere in the universe until relatively recently, when enough stellar generations had enriched galaxies with heavy elements. If true, Earth's habitability might depend partly on the Milky Way reaching a metallicity threshold that suppressed gamma-ray burst rates enough for evolution to proceed uninterrupted. Life exists because the cosmic firing squad stopped aiming here. As of 2024-01, no mechanism exists that could protect Earth from a sufficiently close, sufficiently aligned gamma-ray burst. No shield, no warning system, no evacuation plan. The physics forbids early warning because electromagnetic radiation carries information at maximum speed, and gamma rays are electromagnetic radiation. If it happened tonight, the first indication would be satellites going haywire as electronics fried, then aurora at all latitudes as charged particles poured in. Then, over months, the ozone would thin, the UV would climb, and the slow dying would begin. The odds say it won't happen. The physics says it could. And that gap between statistical safety and fundamental vulnerability might be the most honest description of humanity's place in the cosmos. The universe is not hostile, it is indifferent, and indifference at cosmic scales can look exactly like hostility to anything small enough to be erased. Like if this was interesting, hit the subscribe for more and turn that notification bell on.